Remember this?
Yeah.
So this is f composed with g. And what it means is we're going to take x, plug it into the inner function g, get a value, if x is a numerical value, and then plug into f, whatever we get when we find g of x. So we work from the inside out. Now, when it comes to domain of composite functions, a couple things must be true. One, any x not in the domain of g must be excluded. So you take that inner function, and right off the bat you have to exclude anything that would make the inner function undefined. Okay? Bless you. So that's the first thing we do is we look at the inner function, and whatever would make the inner function undefined has to be excluded in the domain. And then we also look at the outer function as well. So any x for which g of x is not in the domain of f must be excluded. So remember, we're putting g into the x in the f of x function. So anything for which g of x is not in the domain of f must be excluded. I'll show you what I mean by that in a little bit. I thought I'd start by just demonstrating or reviewing, and this is really a review, what this function notation f composed with g of -3 actually means. I really like to think of it in this way. That's f composed with g, because that really tells me that, yes, I am evaluating this thing from the inside out. I'm going to first find g of -3, right? So g of -3 would be -3 squared minus 5. 9 minus 5 is 4. And so I could replace g of -3 with 4. So first calculate g of -3, then find f of 4. And f of 4 is 2. So f composed with g of -3 is 2. So I'm going to let you try the other two. Note here we're plugging g inside of g. Okay, so and then here I've switched it around, g composed with f. You see that? So you're going to do the inner function here will be f of -2. So go ahead and try that. Right, so this one that does not exist because -2 is not in the domain of f. And then the last one is 11. All right, let's look at number 2. A little more practice here. G of f of x. Here's what this means. We're taking f of x and plugging that whole function in for x in the g of x equation. So f of x is actually x plus 1. So this is the same as finding g of x plus 1. We did this when we were working with the difference quotient. This is what we were doing. So g of x plus 1 means take 2 times x plus 1 minus x plus 1 squared. So 2 times x plus 1 minus x plus 1 squared. And so I'm plugging x plus 1 in here and here. And then we're going to evaluate that. So this is 2x plus 2 minus, this will be x squared plus 2x plus 1. And then if I distribute that negative sign, it's 2x plus 2 minus x squared minus 2x minus 1. Negative x squared plus 1. That's my final answer. Good. All right, g composed of f of negative 5. So this is g of f of negative 5. So f of negative 5 is going to be what? Negative 4. So negative 5 plus 1 gives me negative 4. G of negative 4 then is, might need to write this down, 2 times negative 4 minus negative 4 squared. With all these negatives floating around, it's kind of nice to write this one down. So negative 8 minus 16, which is negative 24. This one I think we could probably do in our heads. F of g of 1. So g of 1 would be 2 minus 1, which is 1. And f of 1 is 2. All right, so that's the composition of two functions. You can actually have more than two functions, one inside of another, and maybe, multiple. Okay. Now, this should be new for you. Talking about the domain of the composition of two functions. I gave you two things that must be true. First thing that must be true, and back up here, is that any x not in the domain of g must be excluded. So let's start our exclusion list here. This is f composed with g. G is the inner function. What are the restrictions on g?
Can't be 0.
Can't be, x cannot be 0. So right off the bat, I can say x cannot equal 0. Remember, we've only talked about two restrictions. No 0 in the denominator of a rational function, and anything under a radical must be greater than or equal to 0. Yeah, so those are the only two restrictions we've talked about so far. In this unit, we're going to add another restriction associated with logarithmic functions. Okay, so we'll have a third one, but we only have two so far. So there's one restriction. Now, what f composed with g means is that we're going to take g and plug it in for x right here. Okay? You with me? So what I have for this function, let's just bring it down over here, is 1 over, instead of x, it's g of x plus 3. I've already taken care of the restrictions with g of x. Now, treating g of x just like its own variable, what must be true about the bottom of that outer function? Oh, you're onto it. But before I even make that statement, I'm going to say g of x plus 3 cannot equal 0. You with me? So that's my first statement, is that the whole bottom of that outer function cannot equal 0. And you're exactly right. That means g of x cannot equal negative 3. Okay. So what does that mean in terms of x? What was g of x equal to? You're on to it, yeah. What is g of x equal to here? Okay, so I can replace this, bring it over here, with negative 2 over x cannot equal negative 3. And I think you're onto the right idea, I think. I don't know if, is it 6? I don't think it's 6. 2 over 3. What happens if I cross multiply here and then divide? Negative 3x equals negative 2. What I would probably do is just swap these two. So x cannot equal negative 2 over negative 3, or x cannot equal 2/3. You see how I did that? There's some layers there. So we started with g of x. Looked at the restrictions on g of x. That's the inner function. And the only reason we started with g of x is because it was the inner function. If I switch it up on you here, g composed with f, then I got to look at restrictions of f first. Then what I did is I put g of x in for x here and looked at restrictions for that whole thing. And then replaced by substitution g of x with what it was equal to. If you wanted to, you could just put negative 2 over x in here. It just looks scary for students when I do that. So I'm better off starting, just from experience, doing this first and then solving from there. Otherwise they freak out because you can end up with some messy functions there. So now, if I want to state this as a domain here, The way they will do it in the textbook, I think I need to talk about this with you because this is new, is they will label it like this. And you need to write this down. You may even need to write some notes on this. Let me group these. All right, so they'll write these fancy brackets. So the domain is the set of all x. Here's how you say the set of all x. That means the set of all x such that, such that is all it is a line, but it's a set of all x such that x does not equal 0, comma, x does not equal 2/3. So it's a way of saying all real numbers such x such that it doesn't equal either of those two. That's how they'll state it in the back of the book when you're doing these problems, so you should understand that notation. So the fancy brackets means the set of all, and then you list the variable. The reason we would list the variable is because if I were talking about range in this case, I would be talking about y. And then you list all the restrictions, and that's probably the best way to do it. Another way you could do this would be with interval notation, and you would have to use unions, right? So you'd go negative infinity up to 0, union 0 to 2/3, union 2/3 to infinity. But I just wanted you to see that in the textbook they're going to do it this way, and so in my solutions, any of them associated with the textbook, I have it written out. Okay? Got to be able to read both. All right. What about this one right here, number 4? What do we start with? What restrictions do we? Yeah, 1 is one of them, huh? And you got that from saying, okay, right here, x minus 1 cannot equal 0. So x cannot equal 1. That's the beginning. But I think there's going to be some more here, huh? Because when I take this function and put it in over here, I also have a restriction in the bottom of that fraction. So right here I have g of x plus 2 can also not equal 0. And so g of x cannot equal negative 2. And g of x is, we're told, is equal to 4 over x minus 1. So 4 over x minus 1 cannot equal negative 2. And here, once again, we cross multiply and solve. So what does x equal? Or not equal, I should say. X cannot equal 3. So my domain is the set of all x such that x does not equal 1 and x does not equal 3. Is it plus 2? Oh, negative 2. I messed up here, huh? Yep, it's right here. So it didn't match. That's a negative right there. So that makes this a... You can't erase it. Oh no, sorry. So yeah, this was g of x cannot equal negative 2, so that's a negative 2 right there. When I distribute, it's negative 2x plus 2. I was going, this doesn't match what I'd gotten when I did it on my own. So that's a plus 2. Subtract 2 over. So x does not equal negative 1. I recognized it as soon as I went to write it down because I go, that doesn't sound familiar. So it's x does not equal 1, x does not equal negative 1. X does not equal what's that? No, because it's g of x, the whole function that cannot equal -2. So in terms of x, I get the x cannot equal -1 from that statement. All right. One more here, number 5. Looking at the inner function on number 5, are there any restrictions on a linear function? It just keeps going forever in each direction. So no restrictions here. But now when I take this and put it in here, g of x has to be greater than or equal to 0, right? Remember, it's greater than or equal to, not just greater than. That's a common error. As a matter of fact, in the logarithm, when it comes to logarithmic functions, that's the only thing that'll change, is this will be just a strict greater than. So whatever the argument is, whatever you're trying to take the log of, has to remain greater than 0. That's going to be our third restriction that we're going to learn about. So if g of x is 2x plus 3, I'm just solving this. And so x has to stay greater than or equal to -3. So the domain, set of all x such that x is greater than or equal to -3/2. My fancy bracket too, kind of sloppy there. Yeah. Good. Thanks. All right. Whoa. Some of you guys, when I look out there, so you guys can't look like that guy. So, it says show that f composed with g of x equals g composed with f of x equals x. This is a way to show that functions are inverses of each other. You did do this last time. Remember the process for finding the inverse of a function? You switch the x and y, solve the y. Well, if what? So if on this one, number 6, it says show that these two functions are inverses. So this is more like a proof. Okay, I'm telling you that if you switch the x and y right here and solve for y, you would get this. So if that's true, they are inverses of each other. So we're going to demonstrate that. So here's what it looks like. F composed of g. So f of g of x means taking this thing and cramming it in, yeah, to the f of x function for x. It's not that bad, though. Watch this. It's not that bad. We're going to plug this. No, it isn't. Because 3 times 1/3 is 1. So this cancels out, leaving just x plus 4 minus 4, which is x. So I just demonstrated 1/2 of the proof. This is a proof that these two functions are inverses. Proofs. You didn't even know it was a proof, so I said it was.
That doesn't mean I like it anymore.
Okay. It's a proof in that we're demonstrating something that we already know. I'm stating that these are actually inverses, and we're going to show that when I take g composed with f or f composed with g, I get x. So let's try it the other way. G composed with f of x. So in this case, I'm going to take the g of x function, and I'm going to replace x with 3x minus 4. Whoa. So 3x minus 4 plus 4 is just 3x, and 1/3 of 3x is x. Therefore, have you seen the 3 dots? The therefore, 3 dots, therefore. It's a thing. Therefore, the functions are inverses. Therefore, the functions are inverses. We have proven that these two functions are inverses of each other.
They didn't want to prove that. Though.
And the process you went through last year was you were finding the inverse when you switched x and y. Now, geometrically speaking, inverses are always symmetric about the line y equals x. Yeah. Talk more about that later when we get to the inverses of an exponential function. All right, it says find functions f and g such that, there's a such that symbol, it's backwards e. F composed of g equals h. If h of x equals 1 over x plus 1. Here's what I'm asking you to do. This is the very beginning of the process. Yeah, that'd be nice. Okay, so here's what we're going to do. Break h of x into two separate functions, an inner function and an outer function. And my inner function is going to be g of x. My outer function is f of x. So we want to start seeing these as composition of functions, okay? So, what parent graph do you see here for h of x? What parent graph do you see? Yeah, it is. And it's 1 over x. So, what's my inner function here? My innermost function, what's replacing x in the parent graph? X plus 1, so that's my inner function. And my outer function is always going to be the parent graph that you see here. Okay, so my outer function, we'll call it f of x, is 1 over x. That's the outer function or parent graph. And right now, I think in calculus, they're learning what's called we'll be learning soon the chain rule. And so it's really important to understand that in calculus that you can see these as a parent graph is the outer function and the inner function is what's replacing x. What parent graph do you see in number 8? Kind of, yeah, but it's not the parabola, it's not squared, it's x4. So it's the parabola that's kind of flatter along the bottom. It's on your yellow sheet. That's as high as we went. Even powers was to the fourth. So that means the inner function is what? So you're telling me the outer function is this, x to the fourth, right? The parent graph is the outer function. The inner function then must be 2x plus 3, what I'm plugging into it, yeah. So if I put this in for x in the parent graph, I get this function. So we're just trying to see one function inside of another. Number 9 is tricky. I didn't give you the parent graph for 9 yet. We haven't talked about
Cosines.
Oh, they were weird.
But what would you guess is the outer function here? It might be easier to think outer function first. Yeah, cosine of something, right? Okay, it is. There's the parent graph, and I did not put this on your parent graph sheet. We hadn't gotten to trig functions yet. The cosine of x, so what's the inner function? X squared plus 1, yeah. So we have a function inside of a function. These are not being multiplied together. There's no such thing as just cosine without cosine of something. So we have cosine of some value, we called it x here. And what's replacing x is x squared plus 1. Okay? Alright. It says the spread of oil leaking from a tanker is in the shape of a circle. If the radius r in feet of the spread after t hours is RT equals 200 square root of t, then find the area of the oil slick as a function of time. So, there's my oil slick.
So perfect.
Right, which is the outer function. It's a circle. What's the area of a circle? R squared. But I gave you an equation for the radius, the ever-changing radius. Because think about it, an oil slick is growing, right? So the radius is also a variable. So it's changing, it's not fixed. So I have area equals pi, and what am I going to replace r with?
200.
I'm going to replace it with 200 root t. And two squared, yeah. But I'm replacing r with 200 root t. And so my new equation is 2 times 2 is 4 with 4 zeros. So 40,000 pi t. And that's it.